Today we are going to discuss about AVL tree. AVL tree, named after the inventors Adelson, Welsky and Landis, is a self-balancing binary search tree. That means it follows the binary search tree properties where the difference between height of left and right subtrees cannot be more than 1 for all nodes. So when we finding the balancing factor of each node, its value should be 1, either 1, 0 or -1. That is the balancing. How to calculate a balancing factor? Balancing factor is the difference between the height of the left and right subtree. So here AVL tree checks the height of the left and right subtrees and assures that the difference is not more than 1. This difference is called balance factor. So balance factor is equal to height of left subtree minus height of the right subtree, or height of the right subtree minus height of the left subtree. If the difference in the height of left and right subtree is more than 1, the tree is balanced using some rotation techniques. If the difference in the height of the left and right subtree of a node is more than 1, for suppose if it is 2, then the tree is unbalanced. So we need to balance this tree using some rotation techniques. So AVL rotation. Mainly AVL tree may perform the following 4 kinds of rotation. Left rotation, right rotation, left right rotation, right left rotation. The first 2 rotations are single rotation. These 2 left and right rotations are single rotation. And the next 2 left and right, it consists of 2 rotation, first left then right rotation, then here right then left rotation. So it has double rotation. To have an unbalanced tree, we at least need to a tree of height 2. Here one of the example is here. Here there are 3 nodes. This is a tree with 3 nodes A, B, C, and balance factor of A is it has no subtree. So its child node has a value of balance factor 0. Then in the case of B, here there is a 1 left subtree and 1 right subtree. So 1 minus 1, that is 0. So all nodes have a balancing factor value 0. So it is a balanced tree. In the case of here, the child node A has 0 balancing factor, B has 1 because its left subtree has 1 and there is no right subtree. So 1 minus 0, that is 1. And in the case of C, balance factor is the left subtree, height of the left subtree is 2 and right subtree is 0. So 2 minus 0 will be 2. So its values, C's value is greater than 1. So this is an unbalanced tree. The same case here, his A value is -2 and here it is -1. So this is an unbalanced tree. So we need to make this tree to a balanced one. For using that, we are using some rotation techniques. So suppose that let the newly inserted node is W and Z be the first unbalanced. Here let the newly inserted node be W. Here newly inserted node W. Then first one, perform the standard BSG. BST is binary search tree insert for W. Then starting from W, travel up and find the first unbalanced node. So let Z be the first unbalanced node. Y be the child of. So this is a tree. Suppose this is a tree. Then we are inserting a new node W to the tree, and W, starting from W, we are travel up and find the first unbalanced node. So this is the first unbalanced node Z. Here this is the first unbalanced node Z, and Y be the child of this Z that comes the path on the path from W to Z, and the W be the grandchild of Z that comes on the path from W to Z. Rebalance. Then here we are consider X. X is the grandchild or child of Y. So suppose here X is the grandchild of Z, or child of Y, comes on the path from W to Z. Then we need to, this is an unbalanced tree, so we need to rebalance the tree by performing appropriate rotation on the subtree rooted with Z. There can be 4 possible cases that needs to be handled, as X, Y and Z can be arranged in 4 ways. The following are the possible 4 arrangements. First case, Y is the left child of Z and X is left child of Y. That is left case. Here Z has a left child of Y and its left child is X. Like this. This is the first case. This is left case. Then next one is Y is the left child of Z. Y is the left child of Z, and X is the right child of Y. So X is the right child of Y. So this is LR case, left right case. Then next one is Y is right child of Z. Y is right child of Z. Right child of Z, and X is the right child of Y. That is R case. Then last case is Y is right child of Z. R is right child of Z, and X is the left child of Y. So RL, that is a right left case. So these are the 4 cases. Here we are using all these cases. We only need to rebalance the subtree rooted with Z. So here Z is the unbalanced, so we need to rebalance the subtree rooted with Z, and complete tree becomes balanced as the height of the subtree after the appropriate rotation. So this is the first case, left case. Here assume that T1, T2, T3 and T4 are the subtree. Then this is the Z. Then Z has a left child of Y and Y has a left child X. Then if this is the LL case, to balance this tree we are perform a right rotation based on Z. So here we are performing the right rotation. So right rotation makes move this Z to move to downwards. So Z is moved to downwards, Y becomes the root, and left child of Y becomes X. And here the Y's right child becomes the Z left subtree, and there is a single change is there. So here Y's right child becomes the Z's left child. Then this is an example here. There is, consider, this is the subtree. The right child node has balance factor 0. Then here it is 0, 0. And 5 has one balancing factor 0. Here it is 10. Balancing factor is, we are selecting the longest subtree path, that is 2 minus 1. 2 minus 1 will be 1. And here it is 3 minus 2, 1. And here it is minus 1. Here it is 0. So all trees are balanced. So we need to insert node value 3. So 3 will be first checked from the root. It is a BST tree. So we are starting from root, and 3 is less than 13. So move to left subtree. So 3 is less than 3. Less than 10. So move to next node. 3 is less than 5. So move to the next left. So 3 is again less than 4. So we insert as a left subtree of 3 is inserted as a left child of 4. So that is here. 3 is added here. Then next we need to find the balance factor of each node. Here starting from 0. Here also 0. Then here it is 1. Then here it is balance factor is 2 minus 1, 1. Then 10 is here 3 minus 1, that is 2. So 2. So balancing factor of 10 is 2. So it is an unbalanced one. So we are check that which case is there. Here it is left case. So we are perform a right rotation based on this 10. So 10 will be moved to right. Then 5 will be now root. So 5. So here it is 10 is moved down, and 5 will be the now root, and remaining all are same here, 13, okay, 15, like that. And 5 is moved to, here is 10, 30, here 13 here. Then 10 is moved to here. 10 is moved to right. So 10 is moved to right. Is right subtree will be 11. Then the 5 becomes now root. 5 becomes root. 5's left subtree is 4 and 3. Then 5's right subtree is 8. So it becomes the left subtree of 10. So remaining all are same. Here it is 13, then 15, then 16. This is the balanced tree. Then next one is left right rotation. So here we are Z has a left child y, and y has a x has a right child of y. So it is a left right. So it first perform a left rotation based on this y. So here it perform a left rotation. After the left rotation, x becomes the root and y becomes the left child of x. Then we perform a right rotation based on, here it is perform a right rotation based on z. So z becomes the right child of x, and x becomes the root and y becomes the left child, and x right child becomes the z left child. This is an example. This is a balanced tree, and when we try to insert node 7, node 7 is inserted here right child as a right child of 6. Then we are checking the balance factor of each node. Then balance factor of 10 is uh, unbalanced, so it is more than 2. So we are checking that which cases is that. Here it is left right case, LR case and LR case. So we are first perform a left rotation based on this 5. So based on 5, there is a left rotation. That means here we are performing a, this is LR. So here we perform a left rotation. So 5 is moved to downward and 6 is becomes the root. So here 6 becomes root and 7 is the right subtree of 6, and 5 and 4 becomes the left subtree of 6. Then here again this is an unbalanced tree. So here it is a L. So we are performing a right rotation based on this 10. So 10 is comes downward and 6 becomes the root. So 6 here, then 10 becomes downwards and 11 is the right of this 10. And here left subtree of 6 is 5 and 4. So it's 5, 4. And here right subtree of 6, that is 7. 7 becomes the left subtree of 10. And remaining are all are same, 13 like that. So this is the balanced tree. So this is the balanced tree. Next one is right case. In the right case, Z has a child right child y and y has a right child x. So y is the right child of z and x is the right child of y, and here it is a right case. So we perform a left rotation. So left rotation means z is moved to downwards and y become the root and x is the child node, and x has two subtree t3 and t4, and the subtree of y, there is y has a left subtree tree 2, that becomes the right subtree of z. And this is an example. This is a balanced tree and we are trying to insert 45. 45 will be inserted to here. that is in the right of the 40. So when we check the balancing factor, 30 becomes unbalanced. So it is a right case. So we move a left rotation based on this 30. So left rotation means 30 will be comes to downward and 35 will be the root. So 35 will be the root and 30 is the left subtree of 35 and 40 and 45 are the right subtree of 35, and here there is a 32 is there, there is 35 left child, that becomes the right child of 30. The next case is right left case. In the right left case, here y is the right child of z and x is the left child of y. And first we perform a right rotation based on this y. There is right rotation based on this y. Then x becomes the y is coming downwards and x becomes uh, uh, x goes to upward, and y has a two subtrees. One is T4 and another one is the right of the T3, and x has only one left subtree, that is T2. And here again we are performing a left rotation based on this Z. So after performing left rotation, Z comes to downward. So Z here, then x becomes the root and y becomes the right subtree, and it has two T3 and T4, and Z has a left child, that is T1, and that left child of T2, that is the subtree of right child of Z. T2 becomes the right child of Z. This is the balanced tree. Then this is a given example. Here we are trying to insert 15. 15 will be inserted as the left child of here 16. So here we are calculating the balancing factor. Then 7 becomes unbalanced. So we are checking this R right. Here we are checking the first unbalanced node from the path of from the path from the new node, new added node. So here we are going from here to here. First unbalanced node is 9. So we are checking that which case is this. So it is a right left case. So we perform first right rotation here based on this 16. So 16 is moved downwards and 15 goes to middle. So is 9, then 15, then 16, like this. That is here. 9, 15 and 16. This 9 is again unbalanced. So here RL rotation. So here we are performing a left rotation. Left rotation means moving to here based on this 9. So here we are performing a left rotation based with 9. So 9 will be moved downwards and 15 move to upwards. And here 7, then is 15 comes upward and 9 becomes the left subtree of 15 and 16 become the right subtree, and remaining all are same. This is the balanced tree. So here perform a left rotation, 9 as the pivot and becomes like here. and this is the balanced tree. So what is the advantage of using height balanced tree? Here it is provide the height of the tree becomes less, so it provide a better search time for keys, and operation like insertion and deletion have low time complexity. Then what are the applications of AVL tree? Mainly AVL trees are used for in memory sort, for offset and dictionaries, and also it is extensively used in database application, in which insertion and deletions are fewer, but there are frequent lookup for data required. So that's all about AVL tree.